positive integer, which is the smallest possible, then this number k is called the order, and we want to study further about this order. First property that we proved was this order. Theorem 8.1 I already proved. This order divides any h satisfying a to the power of h. So if this is satisfied, then k divides h, and the other direction is obvious, right? So this is the one that I proved. In other words, any other h satisfy this condition, then k divides h. And the next thing that I proved was, maybe I can prove this today, theorem 8.2, and if k is the order, then for any number having GCD equal to 1, a to the power of, for instance, I and a to the power of j are congruent mod n, then I and j are congruent mod k, where k is the order. So I will prove this today, and if you have a question about this, ask me. Then let's prove it. So we have this statement that we want to prove. If we divide both sides by aj by cancellation law, then assume that I is greater than or equal to j. So we will assume this thing without loss of generality. And under this assumption, if we divide both sides by aj, then ai divided by aj equals aj divided by aj1 mod n over g, where g represents the GCD. And the GCD of a and g, GCD of a and n is 1. So GCD of this is 1 because GCD of a and n is 1. And then if this happens, then any power, GCD is also 1. I proved this already. So we completely proved this statement. And because of this, we can say that a to the power of I minus j is congruent to 1. Then by the previous property, this number, h, right? This number is h, right? This number is h. And then this h is divided by what? Divided by k. And this means I and j are congruent mod k. So I complete the proof. Any questions? So the previous statement said if we have a power k, then anything satisfying this is divided by k, right? The order divides any h satisfying this condition. And we complete the proof. Any questions? The next thing that I want to prove is the statement like this. Assume that corollary order is k, right? Order is k. Then assume that k is order of a, then a to the power of 1, a to the power of 2, a to the power of 3 up to a to the power of k are incongruent mod n. In other words, because order is k, any less power than k cannot be congruent. That's the crux. And how can you prove it? Assume that somewhere like I and aj are congruent mod n. Then, by the previous property, a minus j is divided by k. But all these numbers are between 1 and k. So the only possibility that this happens is I equals j. Right? In other words, there is no chance that different indices creates the same congruence. In other words, if you have different indices, then we will get different mod. That means all of these are different, right? In other words, if you have different powers, right? If you have different powers, then these cannot happen, because if this happens, then they are the same, right? If they are congruent, then powers are the same. If powers are different, this cannot happen. So we complete the proof. Any questions? The next thing is theorem 8.3, which says if the same condition, right? K is the order of A mod n, and H is positive, then a to the power of h, let's call this capital A, right? Let's call this, so a to the power of some number, some positive integer h, right? And call this A. Then the order of this, right? The order of this number A is nothing but order k divided by the GCD of what and what? H and K. So when you have some power H, then it has the order K over something. As you know, if you multiply A, K times, it's automatically what? 1. That's the definition of the order, right? If you multiply A, K times is 1. But if we have already multiplied H times inside, then the order might be smaller, right? Order might be smaller. How much smaller? This order K divided by GCD of H and K. So I will use my usual notation and then change this thing. So K over G, right? Where G is the GCD of H and K. If you don't understand this situation or this statement, ask me. So we have order K, right? A to the power of K. If we multiply A, K times is 1. Any less power cannot achieve it. But now assume that we have some number capital A, which already have the multiple of A's, right? How many times? H times, right? Then if you have capital A, this number A has order not exceeding K, right? It can be K, but it cannot exceed, because if we multiply A, K times is automatically 1. But what will be the order? Order will be smaller than or equal to K, right? And K over G is the exact order of this number A. So if you don't understand or don't have any intuition about this, ask me. Then let's prove it. So proof that order is K over G. So a to the power of k over g will be done, right? If it's an order, this should be equal to what? If this is the order, then this power should be equal to 1 by definition. If you multiply capital A order times, then it should be equal to 1 by definition. Definition of the order, if you multiply the number, a certain number of times, it is equal to 1. So take a look. The definition of the order, if you multiply A k times, then it is what? 1. Do you see it? So what I want to show is this. We want to prove that this is the order, right? So I multiply A this many times, right? I want to multiply this many times. So let's do it. So before doing it, I will define something. Instead of using fractions, I will define some number. So I will say capital K is, I will say this, because GCD of H and K is G, I will say G times K is lowercase k, and then G times H is lowercase h. Do you follow me? Because of this. They have the common divisor, G. So K is nothing but common divisor, G times some number called capital K. H is G times some number called H. So I will use this notation instead of this fraction. Then because of this, K over G equals what? K over G is capital K. Same way, H over G equals H, right? So in this sense, I can write it this way, A to the power of H. But it doesn't matter in this case because we can cancel. A by the capital A is, by definition, A to the power of H. Right? By definition. Oh, why did I write suddenly H, K? Sorry, this is K. Do you see it? It's H, K. Then, now the next line, I will go to the next column because we don't have enough space. A to the power of HK equals A to the power of H is nothing but G times capital H, and then K is here. Do you see it? And then now I can rearrange it. G times K times H. Then I can write it this way. A times GK and then H. And then GK is nothing but small k. So please check all these steps and ask. Now, the order of A is what? By the given condition, initial condition, order of A is lowercase k. So, by definition, this is congruent to what? 1 mod n, right? This is congruent to 1 mod, by definition of the order, right? This is the order. And if you multiply 1 h times, it's still 1, right? So we showed that a to the power of k over g, it is a little bit strange, so I will use lowercase clearly. K over g is congruent to 1, right? I showed this. Then, by the property that we proved last time, theorem 1, 8.1, the actual order, so let's call the order of let's give a name. What name do you like for the order of capital A? So we want to prove this thing, but until then, I want to name the order of A. So you may pick any letter representing the order of A. So what name do you like? Order of A is called what? In the end, it will be equal to this one. That is the one that I want to prove. But temporarily, I want a name. So what name do you like? Any letter you pick will be used. Any name that is not used, excuse me?
Z.
Right? So we will use this thing, right? So order of A is Z, and then we will show that this is the case. So because of this reason, the order Z divides K over G. Do you see it or not? If you don't see it, ask by the theorem 1. If something, a to the power of h is 1, right? A to the power of h is 1, then h is divided by the order, by the property that I proved in theorem 1, 8.1. Then, the next thing that I want to prove is this. Assume that we have a to the power of z. Then by definition of the order, it should be congruent to what? 1, right? By definition, right? Because we said z is the order of a, so it is 1 by definition. So let's rewrite these things. Then a is nothing but a to the power of h, right? So a to the power of z is this thing. So, because of this reason, as you can see, K divides this power HZ. Do you see it or not? If you don't see it, I will, because if this is satisfied, so, right, if this relation is satisfied, then this power h is divided by, right, this power, generic h, right? Generic h is divided by the order of a. Theorem 1, right? Theorem 8.1 says what? If we see any situation like this, then this h is divided by k. So we saw that situation here, right? We saw that this a to the power of some power is 1. That means that power is divided by k, by theorem 1. Do you see? Then, because of this, we now know that k divides h times z, and we can rewrite k and h using capital letters. G times k divides g times h z, and we can cancel out g, then k divides h times z. Any questions up to this point? Now, what is the GCD of k and h? GCD of capital K and capital H is what? 1, because of this reason, we initially started with GCD of H and K, and then we extracted G, and we created K and H, and then they are now relatively prime after extracting big common factor G. So because of this reason, and by the lemma that I proved before many times, K cannot divide H, then K should divide what? Z, right? Do you see it? So K should divide the Z, and previously I proved that Z divides AK over G, that is capital K, right? So by these two things, we arrived at this situation. Z divides K, and k divides z, and both are positive, then the only way that happens is what? Z equals k, right? Z equals k, or k is equal to k over g. So we complete the proof. So please browse the ideas and check and ask questions. Then the next thing that you want to prove is, it's very simple application of this thing in corollary. The same situation over and over again, corollary. K is the order, right? Order of A, mod n, right? Then the order of A to the power of H is K if and only if and only if the GCD of the order and H is 1. Why? Because if this is 1, then in the previous theorem, denominator becomes what? 1. The denominator becomes 1. So K over G was the order, but G became 1 because of this condition, then automatically the order is K. So this is the corollary. Any questions? So in the previous theorem, I replaced the denominator G by GCD, and GCD happened to be 1. In other words, the order is K. Then, very important definition, unless you question me. You have a question, I will cover the next important definition. Theoretically, this is a very important definition. Assume that order of A mod n happen to be some number such as phi of n, right? Order of A happen to be some number k, right? That k happen to be phi of n. Then this number is called this A is called a primitive root of n, this mod n, right? This n. So A is a primitive root of n. So this is the definition. In other words, if some number has order phi of n, then this A is called a primitive root of n. If you do not understand the definition, ask. So A is called a primitive root of n when A happen to have the order equal to phi of n, not any smaller number, but possible maximum number, phi of n, then it is called a primitive root of n. And for a certain n, there can be many primitive roots, right? But there could be none. Anything is possible. There could be many primitive roots, or there could be none. And unless you have a question, I will continue and show you examples. But let's look at some example. So pick any number n. Your n will be used. So n equals what? Your n will be used. Your n is what? 7, right? Or maybe composite number, 6. So I chose 6. Then for 6, I want to check possible phi values. So for I running from 1 through 5, I will print out I and phi of, I to the power of, oh, you need to pick A2. So I choose 2, right? So 2 is my I. Then mod I, 2 to the power of I, and then n. So that's the one that I will print out. Then as you can see, 2 to the power of 1 is 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And then 8 is congruent to 2 mod 6, right? And then 2 to the power of 4 is 2 squared, that is 4. 2 to the power of 5 is 8. 8 is congruent to 2. So do you see that this is a primitive or not? Do you see it or not? Any number between 1 and 5 can achieve the right side equal to 1 or not? You cannot achieve it, right? So let's pick another number, 5. So instead of using this number, I will open and then, so A is equal to 5, and then N is equal to 6, and then I will do the same thing for I running from 1 through 5, and I will print out I and mod A to the power of I, and then mod n, right? So I will do this thing and then end. So let's do it. So let's run this thing. I will save this as primitive 7. So let's run it. Then as we run, we get these numbers. First of all, 5 to the power of 1. 8 to the power of 1 is 5. 5 to the power of 2 is what? 1. 5 to the power of 3 is what? 5. Do you see it? So in this case, do we get the primitive root or not? Oh, by the way, I will show you phi of 5. Phi of 6. Phi of 6 is what? Can you guess phi of 6? Can you guess phi of 6? Phi of 6 is 2. If you don't know phi, then remember this thing. When you are asked to calculate phi of 6, then it is 6, and then 6 equals what and what? 2 times 3, right? So 1 minus 1 over 2, 1 minus 1 over 3. So this is the calculation. Then 6 times 1/2 times 2/3. So we can cancel out these things to get 2, right? Phi of 6 is 2. I did this at least 5 times here. With computer, more than 10 times here. So phi of 6 is 2. So take a look. 5 to the power of 1 is 5. 5 to the power of 2 is what? 1. So is 5 a primitive root of 6 or not? Is 5 a primitive root of 6 or not? By the definition, it's a primitive root. Why? Because of, for instance, 5 is a primitive root of 6. Why? Because 5 to the power of phi of 6, 5 to the power of phi of 6 is congruent to 1 mod 6. And this is the smallest possible number giving the result, right? 5 squared is 1, right? 5 squared is 1. But before this number, it doesn't happen. So it's called a primitive root. Let's pick another number. You may pick some number, some 2-digit number, then I will use it. So pick 2-digit numbers. What 2-digit numbers do you like? Any two-digit number will be used. 33 is the number that you chose. Then primitive root a should satisfy what? And then this power should be the smallest power achieving it, right? Any smaller power achieving it disqualifies A, right? Do you see it? Any small power then phi of 33 disqualify A. Then we should pick different A. So for this number, I will use the calculation. How can you calculate phi of 33? It is equal to 33 multiplied by what? 1 minus 1 over 3 and 1 minus 11, right? So 3 times 11 is the prime factorization. Because of this, it is 33 multiplied by 2 over 3 multiplied by 10 over 11. Then it is 20, right? So if we achieve this thing by multiplying a 20 times, but no less than 20 times, then it is a primitive root, right? Do you see? So let's check it. So I will run the same program. N is 33 chosen by you, and A is like any number, like 2. Then let's do it. 33 minus 1, right? So I will do this thing. I running from, right, this is the one that I will do. Now let's run it. So let's run it. Then, as you can see, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 3 is 8, 4, 16, 5, 6, 7, 8, 9, 10. So is 2 a primitive root or not? Is 2 a primitive or not? So yes or no? Yes or no? How many say yes? Yes, no. It is no. Why? Because to be a primitive root, the order of A should be exactly phi of n, which happen to be 20, right? If order is less than this, then it cannot be a primitive root. Do you see the definition? In other words, we achieved this one when it is not 20. When it was 10, I could achieve it. In other words, it is disqualified. In other words, 2 is disqualified because of the region here, right? Because of this, 2 is disqualified. 2 cannot be a primitive root. If you don't understand, ask me. So if 2 is a primitive root, the only way possible is 2 to the power 20 is the first appearance of A, right? 1, right? 2 to the 20 is 1. Before that number, it cannot be 1. So 2 is disqualified, so I will use 3. 3 is not relatively prime, so 4 cannot be because already 2 is disqualified, right? 5. So let's check 5. Now let's run it. Then this happens, and then 2, and then 3, 4, 5, 6, 7, 8, 9, 10. Is it a primitive, is 5 a primitive root or not? Impossible, right? To be a primitive root, we should get the right side equal to 1 only at 20, not any number smaller than 20. It cannot be a primitive, so disqualified. And next number, 5 is disqualified, then 6 is not relatively prime, 7. So let's run this for 7. 7, then as you can see, 1, power 2, power 3, power 4, power 5, 6, 7, 8, 9, 10. As you can see, it's not. So as you can see, in fact, there is a powerful theorem that I will introduce later. For 33 that you chose, we cannot have any primitive roots. Sometimes primitive does not exist. Primitive does not exist. So I didn't choose this number. You chose this number. For the number that you chose, no matter how hard we try from 2 through the end, we cannot get the primitive root. So 33 doesn't have any primitive root. So it is a little bit unlucky to have this thing. Pick another number. So I will pick another number instead of you, because I know what numbers do not give us primitive root. I will pick some number that will give us primitive. 18. I will pick 18. So 18 gives us a primitive root, but we don't know what number is the primitive root. So with 18, I will use, for instance, some number relatively prime to 18. So 5, right? Let's use 5. So I will run it. So as you saw, primitive root may not exist for a given number n. You chose 33. For 33, primitive doesn't exist. So let's run it. So first of all, I will calculate phi of 18. Phi of 18 is equal to 18 multiplied by 1 minus, what is the divisor? 18 equals 2 times 3 squared. So 1 minus 1 over 2, and then 1 minus 1 over 3. If you don't understand this, ask me. I did this calculation, as I mentioned, more than 10 times before. So it is 18 multiplied by 1/2 multiplied by 2/3, and then it is 6, right? So if we achieve 1 by multiplying a certain number 6 times, then it's a primitive root, right? But if it is achieved earlier than 6, then it is not a primitive root. So let's do it. So I pick 5, and then I will run it. So let's run it. Then take a look. 5, 7, right? Second power, third power, fourth power, fifth power, sixth power. I achieved this thing at exactly sixth power, but nothing less. Do you see it? Anything less than sixth power doesn't give us 1, right? We don't count 0. We only count positive numbers. So for positive powers 1 through 5, we couldn't achieve it. But when we reach 6, we achieved it. Do you see it? So because of this reason, it's a primitive root. So I will write it. Five is a primitive root of 18. The previous fact, 33 doesn't have a primitive root, right? 33 doesn't have a primitive. 18 has a primitive root, and 18 has, for instance, 5. Is 5 the only one? No. There are more than just this number. There are more than just this number. So I will examine a few more numbers. And in fact, later we will cover a theorem mentioning about the number of primitive roots. Is 5 the only one, or should we search further? And the answer is search further, because if we search further, then we can find more primitive. That kind of theorem will be covered very soon. But in any case, let's find another one. So one number is relatively prime to 18. 2 is the square of 3 is 7, right? So let's run with 7. So if we run it, then 7. So let's look at it. Power 1 is 7, power 2 is 13, power 3 is 1. Is 7 a primitive root or not? No, because we achieved this one way earlier. It should be achieved at exactly 6, not any number before. So 7 is disqualified. Then what number can you find? 7, 8. 8 is okay. 8 is not okay. 9, 10, 11, right? So let's do it. 11. Then, as you can see, power 1 gives us 11. Power 2, power 3, power 4, power 5, power 6. Do you see? So 11 is a primitive root. 11, right? 12 is disqualified. 13. Let's check 13. So with 13, we can see these things, right? So 13, right? And then third power already achieved this, so it cannot happen, right? So 13 is disqualified. Then what number? 13, 14. 14 is not relative prime. 15 is not relative prime. 16 is not relative prime. 17, right? So let's run 17. And then as you can see, 17 will not be a primitive root. 17 is not a primitive root. Why? Because we achieved this way earlier. So we have found just 2, right? And there is a theorem mentioning this thing very soon. In other words, once you give me a number, then I know how many primitive roots exist if there is a primitive. If there is no primitive root, then we don't have to worry. Like 33, right? There is no primitive. But if a primitive root exists for that number, then I know how many. So let's summarize it. If you want an answer, then I can answer before proving anything. But this is the summary. N for N. Primitive root may or may not exist, right? And we, in fact, completely know when primitive root exists. Do you want the answer or not? If you want an answer, I can give you an answer. For one number's primitive root exists, but for one number's primitive do not exist. I can answer if you want. You don't. So, I will say that primitive does not exist when we have these numbers. So, if n is 2, so I will say exist here, right? 2, 4. So I will say that for this number it exists. 2, 4 it exists. And then any odd prime power. Odd prime power. And then 2 times odd prime power. So all these numbers, primitive root exist. All of these numbers have primitive roots. Except these numbers, primitive root does not exist. So now may disappear, right? Primitive root exists, right? Primitive roots exist if n equals 2, 4 or odd prime power, or 2 times odd prime power. Otherwise, primitive root does not exist. Right? So this is the summary. So we have this situation. For instance, 33. 33 is equal to 3 times 11. 3 times 11 is in the left column or right column. 3 times 11. left column or right column. So primitive root does not exist. What about 18? 18 is 2 times 3 squared. So on the left column. In other words, once you see the number, you know whether primitive root exists or not. Yes?
You said that there's a way to find out how many derivatives?
Yes, that will be covered in this direction. Yeah. So once primitive root exists, we know how many. If it doesn't exist, then you don't even have to care, right? So give me a number, then I can tell you whether primitive root exists or not, even how many exist or not. In any case, 33 is in this column, right? And then 44 is also in this column. And then 111 is in this column, right? 121 is in this column, right? I'm just giving you examples. Not already I completely categorized. Primitive root exists for these numbers, doesn't exist for these numbers. So you may check. Then how many is the next question? So how many it exists, right? If it doesn't exist, how many? Answer is 0. Because it doesn't exist, right? Answer is 0. Because it doesn't exist. But in this case, it exists, and how many? Exactly what? It is phi of n. Phi of n. This is the secret behind it. For instance, 18, then phi of 18 is what? Phi of 18 is 6. And then phi of 6 is what? 2. So how many? 2. That was the reason why we got 2. In the past, you didn't know the reason. Now you clearly know the reason. So you may pick any number, then I will check whether primitive root exists or not, and then I will tell you how many primitive roots exist. So I will show you, and then I will prove the statement later. So please give me any number n. Any number is okay. Any 2-digit number will be accepted. 67. Then it's prime power, right? As odd prime. So primitive root exists, right? Right? Do you follow me or not? Prime power. Odd prime power is the case. Because of this reason, primitive root exists. And how many? Phi of 67 should be calculated, and it should be 66, right? And then phi of 67 or 66 should be calculated. Then 66 multiplied by 1 minus 1/2, 1 minus 1/3, 1 minus 1/11, right? Do you see it? 2, 3, 11 product. So this is the phi function. Then it is equal to 66 multiplied by 1/2 multiplied by 2/3 multiplied by 10/11, then it is 20, right? So there are total 22 primitive roots. There are total 22 primitive roots. Total 20 primitive roots. So let's check it. 67. 67, and then I will start with 2. 2. So let's run it. 67 was the case, right? So first thing that we can see is 1, right? Power 1, power 2, power 3, power 4, 5, 6, 7, 8. We cannot achieve it until what? What? We cannot achieve this until what power? 66 power, right? So if we achieve it earlier than 66 power, then it cannot be a primitive root. So look at the second column. Look at the second column and then see whether we see 1. We still don't see 1, right? We still don't see 1. So almost there. We still don't see 1. And then as you can see, 66 power 1. So because of this fact, Is 2 a primitive root of 67 or not? Yes. So because of this reason, 2 is a primitive root of 67. And how many more can you find? Total 20, right? So the numbers satisfying this kind of thing is total 20 numbers, right? 20 numbers satisfy this condition. I don't have enough time to cover it, but you can run and then check and then find all possible primitive roots. Then, what's next? Prove it, right? Prove it. So, as I mentioned before, no matter how many numbers you do and then make tables, you cannot cut it. The only way is proving it. So, first of all, I will prove very simple thing. That is, in essence, the proof of the statement that I mentioned. So it's theorem 88.4, and this is essentially the proof of the number of primitive root. So it's very close to we were very close to this fact already. We felt it's very strange, but we are already very close to the fact. If GCD is 1 and A is a primitive, right? So this is the condition, right? It's a fair condition, right? A is a primitive root, and GCD of A and N is 1. Then A to the power of 1, A to the power of 2, A to the power of 3, up to A to the power of phi of n are incongruent. It is very similar to the previous case that we proved, right? We said that these are incongruent, right? So let's prove it. Assume that A to the power of I is congruent to A to the power of j mod n. Then, by the fact that we proved, we can divide everything by A to the power of j, right? We can divide everything by A to the power of j. That means A to the power of I minus j is divided by k. But k happened to be the order, and order happened to be p of n. In other words, the only way to achieve this is I is equal to j, right? In other words, they are incongruent. So almost identical proof as the one that I gave you, right? I don't have enough space, so I just mentioned. So this is the way we prove it, right? If this happens, then I is equal to j, because what? If you divide both sides by a to the power of j, then I minus j. Then I minus j is nothing but what? Phi of k multiple, right? But I and j are less than phi of k, or equal to phi of k. So it's impossible to get phi of k, phi of n, so it should be 0, right? In other words, I and j are equal. So that means what? The only way to achieve the congruent one is starting with the same number. If we have different starting, then we have different end. In other words, they are incongruent. How many incongruent numbers, as you can see? From 1 through what? From 1 through what? Phi of n. So total number of this thing is P of n. So this is the first part. And the next part is among these P of n numbers, I will calculate the order. So we have a to the power of 1, a to the power of 2, a to the power of 3, a to the power of 4, and so on up to a to the power of phi of n. So these are the numbers that we have, right? Total phi of n numbers. Then, can you calculate the order of each number? Order of this is what? Order of this is phi of n over GCD of 1 and n, right? GCD of 1 and n. I usually use the G, right? GCD of 1 and n. And order of this number is GCD of 2 and n, right? So I'm counting the order, right? The order of each number, right? And then order of this number generally, for instance, a to the power of like r, then order of this number is phi of n, GCD of r and n. We already proved this thing before, right? So please check these things and ask. We are calculating the order. Order is nothing but the order k over g. Do you remember? Order k over g. The given order of A, that is k over g, but k happens to be phi of n. So these are the orders of the given numbers, and if you don't understand, ask me. I proved this in 8.3. 8.3 I proved. Theorem 8.3 I proved it, right? Theorem 8.3 I proved it. Order over GCD is the order of this kind of capital A, right? I used capital A. The order of capital A is K over GCD. So K happens to phi of n, and these are. So among these things, how many have denominator equal to 1? Among these things, how many have denominator equal to 1? Among these orders, how many have denominator equal to 1? Only when GCD of KR and N is equal to 1. How can you count that kind of number? We have total phi n numbers, right? Phi of n numbers. Then how many of them has denominator equal to 1 or GCD equal to 1? By definition, phi of that number, right? In other words, phi of that number is the number of numbers having GCD equal to 1 by definition, right? This is the definition of phi of something, right? And then this number is nothing but phi of n out of these many numbers. So we have total box numbers, phi of n numbers, right? Among phi of n numbers, how many has denominator equal to 1? Phi of this number have this denominator equal to 1, GCD equal to 1, relatively prime to n. So this is the proof that the number of primitive roots, so it's corollary, right? It's corollary. If a primitive root exists, then the number of total primitive roots is phi of n. I completely proved everything, right? So take a look. When you have a number, then you know whether primitive root exists or not. In case the primitive root exists, then we know how many exist. If there is no primitive, we also know the number of primitives, 0, right? In any case, we know the number of primitive roots. So once we see the number, we know everything, right? We know whether primitive root exists or not. When it exists, then it's this. So in general, primitive root is, so the number of primitive root is either 0 or phi of n. When do we have 0? When it's in the right side column that I mentioned, right? When it is in the right side of the column. In other words, for instance, 5 times 7, 0. 10 times, 7 times like 11, 0. Only possible cases are 2, 4, and then odd prime power, 2 times odd prime power. For those, we have these numbers. But except those numbers, 0. The number of primitive is 0. So we now completely understand the situation. So please browse your note up to this point and ask questions. If you don't, then I will cover the next section, which is very important. So please browse 8.1 through, definition 8.1 through this part. Then I will begin to cover the next section. you have the opportunity to stop me still, so if you have questions, you can still stop me. Then, the next question is this, 8.2. Theorem 8.5, and then name is called Lagrange theorem. It says, if f of x is a polynomial with highest coefficient relatively prime to n, right? With highest coefficient relatively prime to n. I will use a prime number. Instead of general n, I will use prime number. So in other words, P does not divide the highest coefficient. If P divides highest coefficient, then it means 0, right? Then the order is lower, right? The order of the polynomial becomes lower. So to avoid this kind of situation, we assume that the highest coefficient is not 0, or has GCD equal to 1. Do you see it or not? If you don't see it, then I will re-explain. In other words, we want to create order n polynomial, right? Degree n polynomial. But assume that somehow we pick some number divided by p, then it is equivalent to saying 0, right? So 0, that means it already has less order than we expect, less degree than we expected. So we don't want that. So we assume that the highest order is highest coefficient is not divided by p. So under this assumption, how many incongruent solutions can it have? That is the question. And Lagrange proved that, or mentioned that. So I didn't even mention the theorem. If this is the case, this equation, f has n most n incongruent solutions. Assume that we find one solution, then we can find infinitely many congruent solutions. But we count only incongruent solutions. Then we can find n most n solution. In other words, if you have second order equation with prime modulus, so I will say P is prime, right? Assume that we have a second order equation with prime modulus, then how many solutions can you find? At most 2 solutions. If you have prime modulus, then, and if you have a cubic equation, how many solutions can you find? 3 at most. Not exactly, but at most. If you have like 5th order equation, at most 5. 10th equation, at most 10. Nothing more than 10. We are all counting just incongruent solutions, not congruent, because there are infinitely many congruent solutions. If we have 1 as the solution, then p plus 1 is also a solution, 2p plus 1 is a solution, 10p plus 1, or 100 or 1 trillion plus 1 is a solution. So counting congruent solutions is meaningless. So if you just count incongruent solutions, mod p, then up to the power we can find at most. This is the statement. And I will prove it briefly, unless you have a question about the statement itself. Do you understand the statement? In short, nth order equation have at most n solutions, right? Second order equations have most 2 solutions. Third order, 3. 10th order, 10. Trillionth order equation has trillionth incongruent solution. Then let's do it by induction. Proof by induction. If order is 1, then the equation looks like this. Oh, f of x equals a1x plus a0. And a1, and then p, GCD of this thing should be equal to what? 1. Then we covered this already. A1x is congruent to negative a0 mod p has a unique solution, right? Has a unique solution. We already proved this before. Like, do you remember the Euclidean algorithm using just one column instead of 2 columns? Using 1 column, you can find these things, right? Equal to 1 initially, and then multiply negative a0 later, right? Any questions or not? So this comes from, I might mention this at least 10 times before. A1, what is the mathematical expression of GCD A1 P equals 1? What is the mathematical expression of this? I might mention this at least 10 times. X plus py equals 1, right? Do you see it? With mod p, we can say that this is congruent to 0, right? With mod p, right? Mod p. So I already proved it, and then multiply both sides by what? Multiply the right side by the x by what? Multiply x by negative a0. Then a0, right? So this is the solution, right? This is the solution we can find. So I already proved these things many, many times. So for 1, it satisfies, right? For 1, there is 1 solution. So there is at most 1 solution. In this case, 1 solution, right? Questions? Then, by induction, assume this thing for n minus 1. Assume this for n minus 1. Then, now, f of x, right, is the one that you can use. Then assume that there is no solution. Assume that there is no solution. So there are 2 cases. Assume that no solution, then proof is done. Because at most n, but there is no solution, so it is already done, right? If there is no solution for f, then it is done. Assume that there is a solution, say A. So assume that there is a solution, say A. Assume that A is a solution. Then consider this. X minus A, and then f. Consider this thing. If you divide f by x minus a, then f of x can be written in this form. And so on. And then some number, and then plus some number. Remain, right? So we will get this situation. Do you see it or not? If you don't see it, ask me. So assume that there is no solution, then we don't care. Because we are done, right? Because there is no solution. That means at most n solution is satisfied. But assume that there is 1 solution and say that the solution is A. Then we divide f by this x minus a. Then because of the order, the thing that follows here is what? N minus 1, right? Do you see it? So we multiply this to get n, then n minus 1 and so on, in R. Because A is a solution to F, right? So A is a solution to F. F of A is what? Because A is a solution, what? 0, right? If it's a solution to F, then F of A is 0. So if I plug in 0, then F of 0, F of A, and happen to be 0. And if I plug in A, then A minus A, and then these things, plus R. Because of this, R is what? 0. In other words, F of X equals X minus A multiplied by something, let's call this G in short, right? G has degree n minus 1. If you have a question, ask me. If you don't, then I will continue. Then now, we are essentially done. In case that we cannot go all the way to the end, you may have an idea by this explanation, but if you have enough time, I'll finish. Take a look. F of X is this multiplied by this one, and then this one has only one solution, A. Why? Because if it's not A, if it's incongruent to A, then B minus A cannot be 0, right? Cannot be 0, cannot be congruent to 0. So only way to have a solution for this part is having A. For the other part, by the induction process, at most how many solutions? N minus 1. So it has at most one solution. It has n minus 1 solution at most. That means at most how many? N. That's the end of the story, essentially. And the remaining part is the details using properties. But essentially, I completely mentioned, but because we have enough time, I will say this. Assume that B is a solution. Assume that B is a solution which is not congruent to A, right? B is a solution. Then F of B is 0 because of the condition, right? B is a solution. Then B minus A, and then G minus B, right? G minus B. And this is 0, so B is a solution to G of X. Right? B is a solution to G of X. So if something is a solution to F, then it is a solution to G, unless it is A. That ends the story. In other words, there is no unfortunate situation. In other words, something is a solution to F, but not solution to G. No, it's impossible, right? If it's not A, then it's a solution to G5. So mutually exclusively we can count. So because of this reason, by induction process, F has 1 plus n most n minus 1 solution, right? N most 1 coming from this part, right? 1 coming from this part, and then the other coming from the induction part of G. So F has n most n solutions. So this is the important theorem called Lagrange theorem, right? Lagrange theorem. So let's type it.